So yes, that's the familiar noise to signal people to dial into Kahoot here. Um, just so you know, this is also available for you to do on your own. It's posted as a link on My Open Math, and so you won't use this game pin in order to do it. You'll just kind of it's. I think it's an option. What is it? It's just I think it's the learn mode. Let's just go in there so you're not actually competing with anyone, but you're just going through the process. All righty. So we're coming back here and we're taking a look again at this thing called the central limit theorem. So, which condition has to be met here? The sample comes from a small population. The population is normal or n is greater than 30. The population must be normal. And the other is np greater than or equal to 10 and n times 1 minus p greater than or equal to 10. Which one of those is necessary? We use the central limit theorem for the mean. Not quite sure. Check your notes. So we have three different ideas from the three people here, and none of them were correct. Okay. So the green option here is, in fact, the condition that has to be met if you're using the CLT for a proportion, not for a sample mean here. We'll actually do a few more problems in that area today. The population can be normal, or if it's not normal, the sample size has to be greater than or equal to 30. But if either one of those conditions is met, you can use the central limit theorem. Red, just not correct. Yeah, which formula do we use there? Yep, it's the green one. Standard deviation divided by the square root of n. You were so close over here if you chose red. Okay, the central limit theorem does not apply. Convenience samples to proportions to all small samples to all skewed populations. Where does it not apply? Good. All three of you got the right answer. Convenience samples. Using convenience sample, that's not a random sample. That's not kosher. We're using any of this stuff in statistics here. Okay, so Ta, if you want to go to kahoot.it, you can put in this game pin that's shown here at the bottom of the screen. Ta? I'm guessing he already knows. Yeah, the game pin is down here. Okay. All righty, Sierra taking the lead. Men's weight follow this model here. A normal distribution with mean 190 and standard deviation 59 pounds. Find the probability that 10 men will average more than 250 pounds. So for this, we've got our three distributions here. Since we're dealing with an average of 10 men, what's our standard error going to be? We calculate that. We've got our standard deviation. What's n? What's n? Whoa, 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 whoa. What's n? What's little n? Y'all are freezing up on me. What's little n? 10. 10. Now, the sample size, right? Sample size is n. Okay, so yeah, so 59 divided by the square root of 10. You will need your spreadsheet eventually for this. And in retrospect, I should have given you about twice the amount of time I gave you. So this is on me. All right, so yeah, how do we do this here? Well, first of all, we talked about, and if you really want to see this, and it's a good idea for you to not be able to do it, but also be able to see what you're doing. We're dealing with three distributions here, three different normal distributions here. Here's the one that we're given. It's got a mean of 190, standard deviation of 59. But we're not dealing with just single individuals here. We're dealing with 10 men, an average of 10 guys. So we have a second distribution. Has the same mean, but this is the mean of the distribution of the sample means. So if we're taking a sample of 10 guys, sample of 10 guys, sample of 10 guys, finding the average of 10 guys, average of 10 guys. On the average, the averages of the average should just be the average. Okay. But our standard error here is going to be a little smaller than 59. It's going to be 59 divided by the square root of 10. And what's that going to be? I think it's 20 something. I'm going to guess. Oh, 18. Okay.
18.657.
657. 4. And so now it's time for us to make use of our third normal distribution. This is the z distribution, which always has a mean of 0 and a standard deviation of 1. We're trying to find the probability of 10 men, the probability that the average weight of 10 men will be more than 250. Okay, so that's this middle distribution here, 250. And we want to know that what the probability is that it'll be more than 250. So we have to figure out what this area is. And to do that, we've got to go to our standard normal distribution here. We're going to be finding the area of this tail, but we've got to figure out what this z value is here. And what's our formula for the z value? I mean, it's really the second row. So x bar minus mu over standard error here. So, but the math will be the same. 190 minus, no, 250 minus 190. My bad. 250 minus 190. And that's all over 18.657.4. And what is that z value? It's going to be 3 point something.
$3.2158.
Others get that too? Derek, did you get something different? It looks okay. It looks right. 3.2158.
Yeah.
Yeah. So we're told we found out that this z value right here is 3.2158. And we want to find the area to the right of the z value 3.2158. And how do we find the area to the right of the z value 3.2158?
In the spreadsheet.
Spreadsheet.
Yeah, 0.0006. Oh, yeah.
And there you are. So it's a lot of work. I do have other problems that we will be doing like this, and I've given you 3 minutes to be able to do those things here. It, in retrospect, how could you do this a little more quickly than what I showed you? It's nice to be able to see these three things here. But what's our first calculation that we had to do? What's the first thing we had to calculate? Standard error. Yeah. So we calculated that first. What was the second thing we had to calculate?
Z.
The z. And then what was the third thing we had to calculate?
Spreadsheet.
The spreadsheet value. Yeah. The area to the right of z. And how did we know that it was to the right of z, not to the left?
Just more
Yeah.
than.
These two words here, more than. Yeah. Cool. To reduce the standard deviation by half, what would n have to be to make it so that if we're dividing by the square root of n, what would n have to be for us to be dividing by 2? Yeah. Yeah. So if we're dividing by the square root of 4, what are we dividing by?
This is by half. To divide it by.
What's the square root of 4? 2.
Oh,
Because 2 times 2 is 4. So the square root of 4 is 2. So tell me what the size of this, how much we're shrinking it if we have a sample size of 4. It's half as big. Okay, so this is just taking some of the concepts and kind of turning them on their head a little bit there. Okay, so as sample size increases, the what? Mean of the sampling distribution increases, mean of the sampling distribution decreases, standard deviation of the sampling distribution increases, standard deviation of the sampling distribution decreases. Which of those things happen as the sample size gets big? What did we notice when we were? Yes. No.
there was time.
Two same and the two other same. There's like two on this side are the same part.
No, no, one is mean of the sampling distribution increases, the other is standard deviation.
It's the same to me.
Yeah. So sample size increased last time. What did you notice about that distribution? Did it get wider or skinnier?
Skinnier.
Skinnier. So the standard deviation get bigger or smaller? Smaller. And how much smaller? It goes down as the square root of n. This is good. I'm glad we're going over this. Getting some good reinforcement here. Sampling distribution of a mean is the same as the distribution of the sample, is an imaginary collection of means of for all random samples, is unrelated to statistics. You probably want that to be the case. Tells us nothing about the variation of a statistic. Conceptual question. Okay. It's not the same as the distribution of the sample because the standard deviation gets smaller for the distribution of the sample means. But so let's make sure we understand this here. We had three different distributions that we were working with in the last problem. What's the difference between this first distribution and this second distribution? Give you a hint. What's the difference between those two? The samples. So yeah. What is this? The whole thing. Not the sample sizes. Well, that's the left. Yeah, the raw data is the one to the left. The one to the right is if I take, it's an imaginary distribution that I would get if I took, in this case, 10 random sample. Well, it doesn't tell the size here. If I took a random sample, found its average, recorded that. Another random sample, found the average, recorded that. Another random sample, found the average, recorded that. That would be distributed a little differently. It would have the same mean, but is it wider or skinnier than the previous one? Skinnier. Okay, so it's an imaginary collection of means for all random samples. Okay, so give me a thumbs up, thumbs down. About here? Okay. So yeah, I mean, this is just a way of describing what we did last time. Remember, I had we were taking a random sample of a certain amount, and we were getting a different distribution here. That's a different thing than the raw data. Okay, so if we take all possible random samples from this distribution on the left here, and we calculate their means, it would be distributed according to the thing on the right. No, nope, no, 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 no. So if we, yeah, so, and if I took a random sample of 100 of size 100 from this distribution on the left, and I recorded the average, another random sample, recorded the average, another random sample, recorded the average, and plotted that according to the right there. Tell me, would that be wider or skinnier? Skinnier. Yeah, and that's because this is the thing on the right isn't the same as the thing on the left. The thing on the right is a distribution of sample averages. Distribution of sample averages, not the distribution of the data, but the distribution of averages of the data. See that? Now it's starting to click. Yeah, yeah. And that distribution of averages will get skinnier and skinnier the larger the samples are. If these are samples that are 10,000 each, it's going to be really skinny than if there's samples of size 5. See that? Okay, good. I knew we'd get there. If a sample mean comes from a population that is approximately normal, the central limit theorem states Oh, sorry.
No, I think the app
Okay.
is asking me to pin again.
It's good. Yeah, so the point behind this, it has to be either approximately normal or the sample size has to be bigger than 30. So if it's already approximately normal, sample size can be anything. So if it satisfies one, it doesn't have to satisfy the other. All right, Derek. For a sampling distribution from population with those parameters and n equal 100, find the standard error. You don't even have to calculate it. You can just take a look at which formula and see which formula is right. Okay. Yeah. So yeah, standard deviation divided by the square root of n. So yeah, 25 divided by the square root of 100. That's this one down here. Yeah. Okay. Same idea. Sorry. Does the population have to be normal for a sample size of 50? Yeah. Has to be normal. Yeah. Hmm? Yeah, good question. All right, last one, and then we'll do another one here. For a population described by those parameters. Okay, this is not enough time to be able to do this, but let's all try it nonetheless here. What's the first thing we have to calculate? Standard error. So it's going to be 16 divided by the square root of 60. Let's find that. 1.6, did you say? Okay, so 1.6, 2.065, very good. All right, now we have to find our z value. 260 minus 266 divided by Derek's number. Todd, tell me about the, you have a crinkle in your forehead. Tell me where you're at. Let me see here. So it was 2 point what? Yeah. Someone guessed right or got it right. Derek, my man. Okay. So and so here's our formula here. Okay. Probability the average is less than 260 here. So here's 260 minus the mean, 266, all over the standard error, which is this number, 2.065. 0.0659. So we're going to get a z-value, and I'm seeing a less than here. So do we need to take a look at area to the left or to the right? To the left, yeah. Really? Okay. Yeah. Okay.
It would be equals, well, it's -6 divided by 2.06.
Yeah. Yeah. What you get?
I got -2.90.
Is that what you got as well, Tarek? Okay. And then when you put that into your spreadsheet and find the area to the left. Okay, so yeah, both of you are getting that 0.0018. So I'm gonna have to reevaluate that question there. All right, so you got the right answer there. Ty, you need some more time? Okay. Can I clear it? Okay.
I haven't answered anything.
Okay. Well, you did answer something.
Not the
So-
beginning, but it picked me out
Yeah.
of the game.
Oh, it did? Oh, okay. Let's do another one here as well. This will reinforce things a bit. Okay, so here we go. Here's another one. All right. Gang's all here. Which of the following is not a condition of the central limit theorem? I think what you're meaning for n greater than 30 is that if it's a normal population, then that's not necessarily required here. But the, uh, the most in your face answer is yeah, samples, they don't have, yeah, they don't, in fact, they shouldn't be dependent. They should be independent. Standard error of the sampling means can be found using which formula? You should get this in 10 seconds. Okay. Yeah,
Much.
too much pressure. The height of men is a normal distribution like this. What's the probability that a group of 20 men have a height greater than 72 inches? Okay, so we've got our three distributions here. What's the first thing we got to calculate? Standard error, good. More success. This one here, okay. Value of n here is what? What's n? 20, good. Yeah, do we have our standard error yet? 0 point something.
Oh, sure.
0.03. Okay, and so that goes down here. And what's our z value? It's going to be 2 point something. Cool. And is it area to the left or right?
That right?
Right, yeah.
Yeah, that's right.
Yeah, good. Yeah, so I'm seeing 3 right answers. Very good. Okay, so questions on that? Seeing a little bit more success this time around. So we'd like to see. Okay. Find the probability that a group of 36 seniors have a mean of at least 22. These are ACT scores, which yes are distributed.
How do you know if it's the right or to the left of this one? This says at least.
Yeah, what does that least mean?
That has to be at least 22. But
Which
anything
means,
small,
what does that mean?
less than 22.
If I were to tell you I want to make at least $15 an hour.
So the minimum we have to make.
Ah, okay. Yeah. divided by 6. Okay. And let's see, we want to know, oh, it's at least 22. Okay, so 22 here at least. So it's going to be some z value here. Question is, what's the z value? And what is that? Right, yeah. So we want to know area to the right of a z value being 1.75. Bet it's going to be this. Yeah, 0.04. Okay. Yeah, very good. I mean, just taking a look at the tail as we drew it, do we know that it's not going to be red? Red is 0.96. Does that look like the size of that tail? Way too big, right?
Yeah, on me.
0.61, I would say the same thing. It's got to be less than half, right?
Yeah.
And this just doesn't look small enough. 0.39, 0.04 is the only reasonable guess. So, all righty. All righty. Calculate the z-score for a student with a score of 24. Top row, middle row, bottom row. Which one? I'm looking at all three of you this way. Top row, middle row, bottom row. Our formula sheet on our little formula packet.
We can do part A with this one.
Which one's what?
And we
Good
don't-
question. Good question. Excellent question. Are we dealing with a distribution of sample means, or are we just dealing with one kid? Yeah. So is this the top row, the middle row, or the bottom row? Top row. Yeah, good, Tom. This is a chapter 6 problem. So yeah, 24 minus 20.6 over 4.8. I think it's going to be, yeah, if I had to guess. Oh, it's 0.71. Okay. Yeah. So all this was the top row, 24 minus 20.6 over 4.8. We didn't have to deal with a distribution of sample means for this. So this is 3.4 over 4.8, which I presume is this right here. So. Oh, really? Okay. Oh, no. Alrighty. Okay, calculate the z-score. Oh, for 20 students now. Now are we dealing with a sample mean? Yeah. So this is the numbers are very much the same, but this is very much it's a different question that's being asked. But this is here. Do we have a standard error yet? 1.073. Okay. So yeah, it looks like it's one of the two numbers on the left. Yeah. Yeah, so this one right here.
So the question before this question. Spreadsheet.
Yeah, why didn't we have to use our spreadsheet on this one? Good question.
Because I think it's asking the,
Because it's asking you to calculate.
But we had to calculate the z-score last time, but we also had to do something else that we didn't have to do this time. Find the area to the right or to the left.
mhm.
Here they were just asking for the z-score, so you didn't need to go to your spreadsheet. All right, Derek maintaining his lead. What sample mean for 30 students represents the 80th percentile? Now, I gave you a lot of time to do this one here. So it's like 4 minutes here. So the 80th percentile. Got our three distributions here. Let's create those. It's X. X bar. And let's figure out what this is. Square root of how many students? 30, okay. Let's find out what that is. And lastly, Z distribution. Zero. And one. Now, for an 80th percentile, can I calculate that for the Z distribution? Can I find out what the 80th percentile is for this distribution? Yeah, is it going to be on the left or on the right?
Right?
The right, and it's going to have how much area to the left? 0.8, yeah, 80%, isn't it? So I got to know what's this Z value right here for which 80% of the area is to the left, and how do I find that?
Maybe 0.8 times the.
Use.
You're going to your spreadsheet, but you're using the option that you don't use as often.
Oh, the second
We
one?
want to know what the Z value is. With how much area to the left?
0.2,
To the left?
0.8.
0.8. And what do we get
So we just put 0.8 on the spreadsheet,
for the p-score? Yeah.
0.8416.
Okay, so this is equal to 0.8416, is that right?
Yeah.
Okay, and what do we get for our standard error here?
0.87635.
Okay, so this time we already have our Z value. What we need to know is where is this on this distribution here? So we have an alternate, we have another equation for that. That's the equation on the far right column.
Are we adding the,
Let's plug things in here. 20.6 plus standard error times our Z value. And what do we get?
We got 22.30.
Sounds about right.
Yeah, but we don't have that option.
No, actually 22. No, I'm thinking it should be 21 point something. Yeah. So a couple of you got that. So yeah, what's the order of operations? What do I have to do first here? Yeah, parentheses, but these parentheses don't have any operations inside of them here. So just do this multiplication. Then I got to add this. I have a feeling you did the addition first, Sally.
Hmm?
I have a
Oh,
feeling you
I
did
think,
the,
yeah, that's why I
that's what
didn't.
it was. So um, that should give you this value here. So when you're given a percentile, which distribution do you need to start with, the X or the Z? When you're given a percentile, which distribution should you start with, X or Z? The Z. Because you can find out what that Z value is from your spreadsheet, right? So then you're kind of working backwards from what you're normally doing, right? In most of your problems, you have an X value first, and then you find your Z. This time you were given your Z first, then you had to find your X. Okay. As the sample size increases, what happens to the distribution shape? The other side of the central limit there. Yep. Becomes more and more normal as the sample size increases. Okay. What's the probability the average height of 50 men is between 69 and 72 inches? Ooh, how many X values and how many Z values are we gonna have? It's two, yeah, it's two. Why did it only? I thought for sure it was gonna give you more time than that. All right, let's race through this. Is anybody got the standard error yet? Thank you. That's a lot. What's going to be the Z value for 69? 0. Yeah, very good. Yeah, what was our second Z value? 4? What was it?
Second Z value was like 7.
Yeah, 7 point,
7.07.
yeah, 0.071. Is that just a few standard deviations above the mean, or is it a lot? It's a lot. So I mean, that's like this entire side here almost, which is half the distribution, isn't it? So that was probably your first indication there that that was right.
So we got the Z value 7.07, right?
Mm-hmm.
Do we put that in the spreadsheet?
Mm-hmm.
And then we get one
Yeah.
after that one?
What do you think you're going to get when you put that in your spreadsheet? Yeah, pretty much one.
Yeah, I
Pretty
got
much all, I mean, that's way off to the right, isn't it? So pretty much all of the area is to the left of that. How much area is to the left of 0? You also know what that is. Hmm? Half. If it's centered at 0,
Mhm.
then half is to the left of 0, and the other half is to the right of 0. So it's 1 minus a half.
I don't understand why we're doing minus half.
Ooh, we've done this. We've got, so make sure you get this here. How do we find the area in between two Z values?
Oh, we subtract.
We subtract the areas to the left or of each of those Z
So for
values.
the 0.5, to get the 0.5, we have to do the same process of the Z value.
Say more about that.
Um, so when we find one Z,
Yep.
we got 7.07, right?
Yep.
So to find the other Z, do we follow the same process?
Sure.
Is that
But
gonna
what's going to happen if I have 69 minus 69 up here? What am I going to
Zero.
get? 0. Yeah. So that second
Oh.
one's easy. Yeah. All righty then. Like the post-it note that says thanks. It's all righty. Very nice. Okay. All right. So let's pick up kind of where we left off here a bit. Okay. And all the problems we were working on for the Kahoot, they involved finding standard errors and z values for sample means here. This one's slightly different in that we're taking a look at the world of proportions here. I think we did we get this far? I think we got to this. Hmm? Okay. Pretty sure we got to this point here. So, and as you can see, so this one is very, very similar to what we did before here. The difference is that we're doing we're getting statistics of proportions here. So this would be an example here. Let's say, what do you suppose the percentage is of people in Colorado that, let's make this as non-incendiary as possible. I think of something nobody cares about. What's that? Oh, okay, yeah. Yeah. That's I can't oh God. So percentage of people in Colorado that got pregnant this year. Okay. So it's probably a pretty small percentage. I don't know, maybe 5% at most. Let's come up with a different. Let's see. So percentage of people who I'll just fall back on my usual voted for Trump. So let's say that it's 0.45. So that's our proportion there. the people who voted for Trump in the last election. I think Colorado didn't win for Trump, so I'm placing it slightly below half. And so if we take a sample of 1,000, we're going to get not P, but P hat. And should it be exactly equal to 0.45 each time? No. So yet again,
So the P.
we're, yeah. So this is if I'm taking a sample of 1,000 people, that's a different situation than when I'm taking a look at all people in Colorado. If I'm looking at all people, then it's not a distribution, is it? It's just a number. If I'm looking at all people, okay, 45% voted for Trump. Right?
Okay.
If I'm looking at samples, I can take a bunch of different samples and I'll get a different answer each time. So I'm going to get a distribution of answers, right? They should be centered. What do you think the center of this distribution would be here? What was that? If for everybody in the state of Colorado, 45% of them voted for Trump, then as I take sample after sample after sample after sample and sample and get proportions from each of those samples, what do you think the center of this distribution is going to be? Yeah, yeah, 0.45. So it's centered around P, isn't it? But it's also going to have a standard error. And the standard error there is going to be found with this formula. So this is your sigma over square root of n formula, but for proportions here. Okay. And notice this z formula here. It's got slightly different letters in it, but it looks an awful lot like what you did for sample means. Input. Oh yeah. 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 So okay, so a Gallup survey indicated that 72% of 18 to 29-year-olds, if given a choice, would prefer to start their own business rather than work for someone else. So random samples of 18 to 29-year-olds are obtained today. What would be the sampling distribution when n equals 60? So let's assume that the Gallup survey has given us the right answer for all 18 to 29-year-olds. So this is not P hat. This is P. I'm assuming that the Gallup survey talked to everybody. Yeah, I'm just making that assumption here. Okay. So yeah, I'm assuming here that uh, the Gallup survey refers to everybody. But if I'm just talking to 60 people, is that P or P hat? P hat. Okay. So sample proportion, not population proportion. So proportion of the sample. We're talking to a few people in Colorado, not everybody. Yeah. So what's going to happen as the sample size goes from 60 to 100? Where's my thing here? To 100 to 600. What's going to happen to the distribution? It's going to be skinnier. Yeah, skinnier and skinnier. So this one is the one for n equals 600. This one is the one for n equals 100. And this widest blue one here is for n equals 60. So just like what we saw with sample means, it gets skinnier and skinnier and skinnier the more people you talk to. Okay. And we can describe this standard error here each time by plugging things into our equation here. So this is P, the 0.72. Where did 28 come from? Where's that? Check your formula. Where did that come from? Yeah, 1 minus P. So yeah, 100% minus 72%, that's 28%. That's where that came from. And then where'd the 60 come from? Yeah, it's a sample size. So you put all those things in. Now it's the square root of the whole thing. And that gives you the standard error here for that. Okay. And how would this change if I was finding this for n equals 100? How would these numbers change? Right. The top doesn't change, does it? It's just the bottom. Right. That's what you're saying. Okay, just okay. And you can see how much smaller these things get as the sample size gets bigger and bigger. Okay. According to credit.com, 29% of adults do not own a credit card. Okay, so here I'm assuming that that's the population. Suppose a random sample of 500 adults is asked, do you own a credit card? What would be the sampling distribution of P hat here? You all understand what I mean when I say that? What's the sampling distribution of P hat? I took a
What
bunch of
percentage?
percent of the sample. Yeah. What would those sample percentages look like if I distributed them, if I plotted them on a histogram here? So um yeah, what would these look like? What would the mean be? For a proportion? Yeah. 500 is the sample size. What should the mean proportion be? Okay, let's take a step back. So, what's being talked about here? What's this problem all about? Yeah. What specifically are we measuring? 29% of adults, what? Do not own a credit card. Okay, so then we're assuming that's the population. We're taking a random sample of 500 adults and we're asking them, do you own a credit card or do you not own a credit card? We're recording out of 500 the proportion of them that don't own a credit card. And then we do it again. We sample another 500 people and we ask them, do you own a credit card? And some will say no. We write down the percentage there of those who say no again. And we keep doing that over and over and over again. So we get this distribution of answers, one from, you know, one answer from each sample of 500 adults. What should be the center of that distribution? On the average, what should they find? If on the average 29, if 29% of adults in all don't own a credit card, then on average, what should we find when we're sampling 500 people and asking them, do you own a credit card?
21% of the 500 adults.
Yeah. On the average, 29% of them should say, yeah, I don't own a credit card. So the center of this distribution here is 0.29. That part's easy. Okay. This here requires a formula. That's this thing down here. Okay, and so we get 0.0203. So that's the probability distribution here. Oh, and before I do this, I have to check that we can use a normal distribution here. So I have to check these things here. This has to be bigger, greater than or equal to 15, and this has to be greater than or equal to 15 right here. Well, N is 500, and P is here, and this is P here. So the fact that N is 500 means it's going to easily, we're going to get something easily above 15 both times. So this means can use normal distribution. And that's all the stuff we've got going on to the left here. Okay. What's the probability that in a random sample of 500 adults, more than 33% of those sampled will not own a credit card? Okay, so remember that's, if we take a look at our distribution here again, P hat, this is centered around 0.29, and I think we got, yeah, this, we calculated this as being 0.0203. That was the previous slide here. We got this value here from our formula. Okay. We want to know what's the probability that with a sample of 500 adults, are we going to get more than 33% of them saying they don't own a credit card? Okay. Well, in order to find that, we need to calculate our z value. 0.33 minus 0.29 divided by this gives me this. And so this is my z value. I have to know what the area is to the right of that z value, and I get this. So let's be clear on what we just found here. We talked to 500 adults. Is it possible that we're going to get 33% or more of them saying they don't own a credit card? Ooh, turn math brains turned off. We're talking to 500 adults. Is it possible that out of those 500 adults, they're going to tell us more than 33% of them are going to say, yeah, I don't own a credit card? You don't think so? You might be thinking that it's unlikely, and you'd be right. But there's a difference between impossible and unlikely. If 29% of the people in Colorado don't own a credit card, and I sample 500 of them, is it possible that I'm just going to get an unusually large number of people there?
Yes.
And it's unlikely. That's the probability that that'll happen. So 2%, 2.5%. 2.5% of the time,
They will say
2.5% of the time, you'll get a sample of 500 people where 33% or more of them say they don't have a credit card. Yeah. Even though the actual answer for everybody is 29%. Yeah, exactly right. Good. Okay, so how about this one here? What's the probability that it's going to be between 25 and 30%? Well, here again, the center here is 0.29. And these are p hats. I think this number is 0.0203. And we want to know what's the probability that you're going to get anything between 0.25 and 30% is going to be over here, isn't it? Hmm. So I've got two z values here. And I'll have to find the area in between those two z values, won't I? Somebody have that first Z value here. It's going to be something negative.
Let's say 0.4.
Excellent. How about Z2? It's going to be positive. Point
0.4926.
26. Excellent. So we have to find the area in between the two Z values. Okay, what is that area?
Well, 0.496 minus plus.
So you're right to be thinking about subtraction, but what is it that we're subtracting? Is it the Z values? Or are we subtracting the area to the left of those Z values?
The area.
Yeah. So how do we find the area to the left of each of those?
And then we add them. No?
You were right about the minus part,
Uh-huh.
you know.
Oh, okay. Mhm.
Okay, so what I see us getting here is
Oh, we have to put in the formula, right? In the spreadsheet. Okay.
660. Yeah. Yeah, very good. Good talk. But make sure you understand where each number came from here. So if I put in 0.4926 into my spreadsheet for Z, what's this? Area to the left. Okay. How about this? If I put this in, that's also area to the left. So I subtract those two off and I get area in between. All right. All right. Let's keep going here. Would it be unusual for a random sample of 500 adults to result in 125 or fewer who do not own a credit card? Now, this one's a little weird, isn't it? Because I'm not giving you a proportion, am I? What's P? The question is, what's P hat here? It's got to be a number between 0 and 1. Hmm? That's P. What's P hat here? What is P hat? What does P hat stand for?
A sample. It's like a portion of the sample.
Proportion, yeah, sample proportion. So for this one, what is the proportion of this sample that doesn't own a credit card? That's the number of people who don't own a credit card. What's the proportion that don't own a credit card? What is it? Now you're looking at the top. You're not looking at the sample. Look at the sample. That's the number of people in the sample. What's the proportion of the sample that doesn't own a credit card? Yeah, 125 divided by 500. Right? So what's P hat? 0.25. Everything else is the same. You just had to calculate the P hat. So again here for my P hats, they'll be centered around this. I think we calculated this to be that. to result in 125 or fewer. So am I shading to the left or to the right? Left. Good. 125 or fewer. Okay. Did that kind of quickly. Yeah, that was calculated on a previous, like 2 or 3 slides ago.
Oh.
Yeah. That was our formula with the square root and the, actually let's recalculate it here. So it's P times 1 minus P. All over N, right? So whatever that is. Did I get that right?
Zero point zero two zero two.
Yeah. 0.020.
Two.
Does it round up?
Oh, three.
3. Okay. So that confirms that, yeah. That's how we got that number for the standard error there. Okay, what's our Z value? It's gonna be negative 1 point something. It's 1.97. 0.04. And again, are we looking at area to the left or the right? To the left. Or 4. Okay. So read the question silently again. What's the answer?
Is that 0.0244 or 4?
Or 4.
Okay.
Derek, what do you think? Okay. What did we find was the area to the left of Z? Was it a little or was it a lot? Little, yeah. So like 2.4%. What are we finding there?
From the spreadsheet?
So say again.
From the spreadsheet. We put the
Yeah, so you
area.
got that from the spreadsheet. That's right. Yeah, that's right. So what are we finding there? That's the probability that we get a proportion less than 25% when we're sampling 500 people. 0.024. Yeah. So read the problem. What's the answer? Yes or no?
Yes.
Yeah. Why?
Because resulted in one to
Out of the 500 people.
of the one to
The probability that that could happen, that 25% or less will not have a credit card is 2.4%. So 2.4% of the time, that'll happen. Okay. What is the percentage below which we would expect an average of a random sample of 500 adults to only occur 8% of the time? Ugh! So this is where it really gets a little crazy. Because this percent means something very different than this percent. But here again, we're getting a distribution of p hats. It's centered around 0.29. And we have our standard error here, which is 0.0203. We don't have to calculate that again. And we also have our z distribution. What's the probability of something that only occurs 8% of the time? 0.08. What is the percentage below which, so where on this z distribution here, can we make a mark where the z values would only be lower than that 8% of the time? How do we find out what this is here, what this z value is? For which the area to the left is 0.08. How do I find that? Yeah. Yeah. So go ahead. Somebody find it. Yeah. Be careful. Do we have a z value or are we trying to find a z value? Yeah. And how much area is to the left? 0.08. Yeah.
0.08 or 0.0? Okay,
So what's our z value? Should it be positive or negative?
negative.
Negative, because it's on the left-hand side. Yeah.
Negative 1.4050.
Negative 1.4050. Good. So now we got to figure out where that is on this distribution here. The formula in the lower right of your formula sheet there. So here we're trying to find a p hat.
Power on.
That's standard.
The 0.0203.
Looks like.
I mean this? The z?
It's P plus.
Standard error, yeah. Times z. Yep. So okay, so yeah, what do we get there?
Zero point 2614.
Okay, statisticians, what did we just find?
Average of wait, hold on. They're not on the 26% of the 8%. No.
Yeah, and some of our previous problems.
Makes me think that 14%, we would expect an average of random sample of 500 people, thus only currently.
Well, yeah, that's right. I have a feeling you're just spouting words. That's right. So we're taking samples of 500 people over and over and over and over and over again. Sometimes it's slightly more than 29%. Sometimes it's slightly less. And in some of our previous problems, I asked you, like, what's the probability that it's going to be less than 0.27? Ooh, everybody's staring off into space. Are we good? I'd ask you, what's the probability it's going to be bigger than 0.27 or smaller than 0.26 or bigger than 0.31? But we were asked what those probabilities were. This is the opposite kind of question. What's the threshold below which you're only going to get that 8% of the time? So if we repeated the sample many times, 8% of the time that we do that, we should get something below 26.14%.
It's exactly what
It's actually true. So if we're doing this same experiment repeatedly, a gazillion times, taking all these samples, stay with me, Derek. You got it? Yeah. So if we're doing this, there will be times in which we get a percentage from our random sample of 26.14%, even though the right answer is 29%. How often will that happen? 8% of the time. If we changed that to 2% of the time, then we'd probably have to go farther over here, wouldn't it? So only 2% of the time would we get something below, I don't know, 21%, something like that. Takes a while. This is a tough concept. Okay, so give yourself some grace here. Yeah. And part of what makes this confusing is that this 29% means something very different than the 8%, doesn't it? 29% of adults versus 8% of the time. So, yeah. So students have, gotten hung up on this slide for, ages and ages and ages. Okay. Just as a reminder, when we're doing this, we're approximating what is really a binomial distribution with a normal distribution. And if you recall, we have to make sure that this is true and this is true so that we know that we can use the normal distribution, which is easier. But here's something to keep in mind. And it has to do with how we handle a discrete distribution versus a continuous distribution here. Okay, so oops, oh, nice. Okay, so if I'm wanting to know what the probability that x is less than or equal to 8 is, and I'm smoothing this over. Where am I? If I'm smoothing this over with this nice, pretty normal distribution here like this, and I want to know the probability that x is less than or equal to 8, should I slice it here exactly? I would say no, because an entire whole thing here. 7.5 to 8.5, then 8.5 to 9.5. These are the boundaries for each one of those discrete separate categories here. So if I blow this up, um, what is the probability that x is greater than or equal to 8? I want to include all of this um, this bar here. And so in reality, my cutoff point isn't going to be at x equals 8. It's going to be at x is greater than or greater than 7.5. I want to include 8 and everything bigger than 8. And so I'm actually cutting it halfway in between 7 and 8. Oh, I feel like I lost you a little bit there. So, yeah. So, let me put it this way. If this were just the probability that x is equal to 8, that would be just this bar, wouldn't it? The area under that, underneath that bar. But here's the problem. If I convert this to z values, and I'm looking at a continuous distribution here, what's the probability of x being equal to 8 when it's a continuous distribution?
Okay.
X being equal to anything for a continuous distribution. Remember, it was all about where you sliced it. From here to the exact same place. How much area is in between those things? 0. Well, that's not really what we want. So what we want to do is, as we're approximating this with a normal distribution, we want to try to get this portion right in here of the normal distribution, don't I? So I want to get the portion that's represented by this side and this side here. This is 7.5. What's this? 8.5. So when I'm translating this to the normal distribution, what I really want is for the computer to give me this. You see that? Yeah. And along the same lines, if I want to find out the probability that x is greater than or equal to 8, well, I want to include 8, and I want to include all these things above 8, so the place where I stop is here at 7.5. And if I, for example, want to find out what's the probability that x is less than or equal to 8, that's still going to include 8, but it's going to include all these others here as well. So I'm actually going to cut it off here at 8.5. It's the continuity correction factor here. Okay. For the following examples here. So what would it be for x equals 7? So think of the bar at x equals 7. No, it should be in between two things.
Oh, I think we'll-
There it is. Yeah. Got that? Okay. X is less than 7. So where's the dividing line going to be between what number and what number? X is less than 7. Will it include 8? No. Will it include 7? No. Will it include 6? Yeah. So in between 6 and 7 is what? 6.5. Yeah. Okay. For this next one, will it include 8? No. 7? Oh, okay. What's halfway between 7 and 8? Yeah. See that? How about this one? Is this going to include 8? Yes. Will it include 7?
Yes.
Yes. Will it include 6? Okay, so it includes 7, but doesn't include 6. What's halfway between 6 and 7? 6.5, yeah. You're like, is it really that easy? Yeah, that's right. It's really, that's right. That's right. So, for the next one, does it include 8?
Yes.
Yes. Does it include 7? No. Okay. Halfway between 7 and 8? 7.5. Okay. X is equal to -2. So what's that? No, you can give an answer. So it includes -2, but it doesn't include -1 or -3, does it? It doesn't include anything on either side. So what's halfway between -2 and -1? -1.5. And what's the boundary on the other side? -2.5, not positive. Nope. So I'm just thinking of the number line here. Oops, that's, yeah. Those are our two cutoffs there, right? Okay, how about the next one? P of X greater than what? Does it include 12? Does it include 11? No, what's halfway between? There you go. Next one.
Zero.
-0.5.
-0.5, right?
Oh.
Yeah.
Why? Because it's less.
Well, let's take a look at it. Does it include, oh, yeah, yeah, does it include -1? Less than 0? Yeah, -1's less than 0.
Oh, okay.
Does it include 0? So what's halfway between -1 and 0?
Okay.
Yeah. How about the last one? So this is a good one. This
Left.
is
Oh,
positive.
-8.
It's kind of hard because on this part of the number line, the numbers are reversed. So greater than -9, does that include -10?
Yes.
No. No. If we were positive numbers, that would be,
It includes -8.
does include -8. Does it include -9? Yes. Okay, so what's it in between? It's in between -9 and -10. So sometimes I have to draw a little picture there. You'll see that. Okay. In a city, 46% of the population favor the incumbent, Don Morgan, for mayor. A simple random sample of 500 is taken using the continuity correction factor. Find the probability that at least 250 favor Don Morgan for mayor. Okay. Let's see, so 250, 251, 249. So probability that at least 250 of them favor Don Morgan. Where's the cutoff here between yes and no? In what two numbers? So does 251 work? Yeah. Does 250 work? Does 249 work? Yeah, it's 249.5. Yeah. So in discrete distributions, we're looking at that. But when we go to a continuous distribution, now we're looking at that. That's our continuity correction factor.
It confuses me.
Well, just go back to that, that same question there. Probability, so X being greater than 250, does 251 qualify? 250? 249? I agree.
Okay,
Yeah, which is why the cutoff is in between 249 and 250. So I asked you if this works, you said yes. I asked you if this works, you said yes. I asked you if this works, you said no. So halfway in between these two is 249.5. Yeah, so you actually know how to do this. Okay, so for a continuous distribution, this is what we're going to be using here for this. Okay, and if it's 249.5, what's our p hat for that? Yeah, 249.5 divided by 500. It's going to be some proportion. It's going to be slightly less than 50%. What's that? 9, 9. One more digit. Oh, 0. Okay,
Oh.
cool. Okay, so we've finally gotten our p hat here. We want to know the probability that p hat's going to be bigger than 0.4990. Okay, well, we have our distribution of p hats. What's this centered around? You actually have the God's eye view here and know what the right answer is. What is the right answer for the proportion of people favoring the incumbent? 46%, yeah. So you have this unusual God's eye view there. So it should be centered around that. We've got to figure out what this is, right? Right, so P is this. 1 minus P is that. And what's our sample size? 500. So find that out, please. Ooh, hearing two different things.
I got 0.0222.
Okay. Let me see if I can. Oh, I don't have it. 0.0222. We'll go with that. And so we want to know the probability that p hat is bigger than 0.4990. Good idea. Very good. Okay. So we want to know what that is. So we need to go to our z distribution here. 0. Now you laughing at my z distribution shape. We want to know the area to the right of some z value. What is that? It's going to be this. 9 minus 0.46 all over the 0.020 or 223. And 488. And what is the probability that z is bigger than that? That z is bigger than that. Very cool. So let's sit back here and figure out. We actually found something very important. Because you have this God's eye view, you know who should win the election. Should Don Morgan win the election? If there's only two candidates. No, she shouldn't win. Why not? She only has 46% of the vote, right? So yeah, she's 4% below half. So she shouldn't win. And yet there's a possibility that when you sample 500 people, you'll get at least 250 or more of them saying, yes, I want to vote for her. In which case the sample would suggest that Don Morgan will lose or win. From the sample, if she gets more than 250, the sample says she should win. So if you're running a sample of 500 people and more than 250 of them are saying, yeah, we want to vote for Don Morgan, you would predict that she'd win, right? But you would be wrong. And what's the probability that you would be wrong? 4%. 4%. Yeah. See how you can use the rules of probability and statistics to try and see what is the likelihood of something going wrong. This is the kind of stuff that they're doing all the time when they're tallying votes in elections and things like that. Well, yeah, I mean, they've got computers doing it for them, but these are the calculations that are coming up here. Okay, so eventually the margins get big enough and enough people have voted, they're like, okay, we can call this. But every now and then they get it wrong. The 2000 election was a good example. I remember 2000. This is before your before all of you were born. I was about to start my PhD program. You were 3 months old, my God. You were just a glimmer in your mother's eye. So, yeah, there was, I mean, I remember the news people came on and said, we're predicting the election for Al Gore. Then they came on a couple of hours later and they were like, we're actually going to reverse that. We think it's George W. Bush. What's that? Al Gore. This is the 2000 election. You're thinking of the 2008. You're thinking of Obama. Yeah. And it was, yeah, yeah, right. So yeah, this was in the 2000 election, and it became a nightmare because there were a bunch of ballots in Florida, of all places, where the basically they had recorded their votes by poking holes in the paper, and there were some places where they had poked holes in two places, and they were like, "Ugh, do we count this? It eventually went to the Supreme Court, and they actually had to decide the election for us, which was very uncomfortable. So, yeah, yeah, that's the only time in our history where that's happened. So, um, but yeah, no, George W. Bush became president. Yeah, so yeah, crazy, crazy. So yeah, it does happen. It doesn't happen very often because they understand the probabilities and they wait until that probability is really, really low. But it never goes to zero, does it? Right? Okay. So, um, check something out here. Some of these problems that I give you are in different, you know, some of them are kind of dark. Yeah. The age range of the prostitutes was 14 to 61. Mean age was 30.9. Standard deviation of 9 years. In a sample of 25 prostitutes, what's the probability that the average age of the prostitutes is less than 35? That kind of thing. So, yeah, you know how to do this. I know. Babies. That's when you're in Jeffrey Epstein land, right? You just
Huh?
Jeffrey Epstein land. So, and there's just a few other examples here. It doesn't look like we'll have time to be able to go through those additional examples here. So we're still looking at the test being on Tuesday for this stuff. Okay. Um, let's pull it up. If people need to go bye-bye, feel free to do that. But here's the practice test here, chapter 6. Oh yeah, you mentioned that there was one you did. It's kind of yeah, 2 times. Was it the last one? Oh no, it was the first one. Oh yeah, this one right here. Quick estimate of the area under this distribution, 68% of the total area is within one standard deviation. So here's the center right here. This is one standard deviation right here. And so let me turn on the annotations here. Well, here's what I want you to see. Here's the center. Would be nice. Why do you choose white? Here's the center. How many standard deviations have I gone here? And how about here? 1. This thing here says that 68% of my area is in one of those, which means how much is in this one? How much in each? 68% in the whole thing. There you go. 34%. 34%. Okay, and I think that's actually one of the questions. I think one of the questions is what's the approximate percentage of buyers who paid between 1470 and 1730? And you already know what that is, right? Okay, so um, for 2 standard deviations, the total goes from 68% to 95%. So how much does that change here? Another 27%? Did I get that right? Going from the area in here, which is 68%, to the area in here, which is 95%. How much more area is that? Hmm? So 27%, let's cut that in half. We don't need our calculator. How much is 26 cut in half? 13. 13. So this will actually be 13 and a half. So that means 13 and a half is here, and 13 and a half is here. And then the last one is 99.7. So how much more is that from the previous one here? I got to subtract off 95, right? That's 4.7. Okay. If I cut that in half, if I cut in half 4.6, what would it be? 2.3. So this is 2.35. Good. So each one of these is 2.35. So each one of the questions down here, let's see, what's the approximate percentage of buyers? Well, okay. And then how do I figure out what this is? This tiny part that's on the end here. It's outside of that. A couple of ways to do it. Yeah, so this is going to go from 99.7 out to theoretically 100. So how much more is half of zero point 0.3? That's right. So this is going to be 0.15. And then I'll explain why. Yeah. Yeah. How did I get that? Yeah. So beyond that, beyond that out to infinity, how much of the area are we hugging when we're going down to infinity in both directions? So I'm going an infinite number of how much of the area am I hugging? Is there any part of it that I'm not hugging?
Yes.
What does it look like? Is there any part of it I'm not hugging?
And look, they're probably, but
Where? Yeah, but I'm going infinitely out in this direction, infinitely out in
that's
this
true.
direction. Yeah. So now I've gone from what was it, 99.7%
Yeah.
to 100%. And how much more is 100% than 99.7%?
0.3.
0.3. And we have to cut that in half. So that's going to be 0.15. So I've got 0.15 over here and 0.15 over here. So each one of these things asks what's the approximate percentage of buyers who paid less than 1340. Okay, so that's going to be 2.35 plus 0.15. See that? So you're just percentage of buyers who paid less than 1340. So you just figure out which things to add up,
Oh,
right? Yeah,
So 2.35 plus 1.5.
plus 0.15. No, 0.15.
Oh.
Yeah.
Okay.
There you go. So what do you get? 2.5. Okay. Okay, if I erase this, make sure you have those areas, copied down somewhere. Or more importantly, know how you got those numbers. Know what you had to do in order to get those numbers.
Add the percentages.
Well, yeah, for example, how did we get 34 and 34? You did that without me. Yeah. Yeah, that's all. Yeah. And then we got the 13 and a half because now we're going from 68 to 95, and that's 27 more. And we've got to split that two ways. So 13.5%. And then we did it again, 2.35 in both directions there. And then lastly, 0.15.
So if it's the.
Yeah. No, am I wrong?
Because I kept answering, that's like, the answer kept answering 0.15 and it kept telling me it was wrong.
Oh,
And like the last one, I thought it was,
did I mess up?
the last one isn't 49.85.
That's on me. That's on me.
Like, I'm
Yeah. Yeah. No, you guys are right. Yeah. Right. But you already know what 1470 to 1730 is. That's within one standard deviation. That's -1 to +1 on the Z. So yeah, that's just our friendly 68% there. Yeah. So what was the other one you were having trouble with? Your last one? Yep, that's right. All right, Withrow screwed up. Withrow screwed up. I will be checking on that. Yeah, I know. You did great. You did great. That's my bad. Y'all are wonderful. Yeah, okay. All right. So yeah, go through the practice tests and the assignments and things like that, and we'll have our test on 6 and 7 on Tuesday. Hopefully, that's the only instance in which the practice tests are run. That's right. See ya.